Today I will talk about an introduction to the Scala programming language, and all of what you're going to see here is based on a book that I've been working on with my co-author Dianne Marsh for the last about a year. And the goal of the book is different than what you'll see with most Scala books. We wanted to try, in the process of researching this, we read through a number of other Scala books, and we took a workshop that was put on by some friends of ours. And one of the things that we noticed is that the language itself is actually very elegant and can be taught simply, but none of the workshops or the books that we saw were treating it that way. Most of them tend to, well, for example, mostly they tend to mention Java on every single page and compare Scala to Java again and again and again. And one of the things that we realized is that this language could be used as a first programming language. It's actually significantly simpler in many ways than Java is. For example, in thinking in Java, I had to spend a lot of time explaining basic concepts before I could start with basic hello world, because there's, you had to describe what a class is and static and all those things before you could do a simple hello world. Well, Scala is much simpler than that when you're just writing a basic program. So what we discovered is that nobody was doing this, and we wanted to make it something that could be used as a first programming language. And so that's what you're going to see here. And those of you who have studied Scala already, this might not be that useful for you, because it's intended, the examples will all be quite introductory. Some things I'm going to assume that I'm going to assume everybody here is a programmer, so some things I will go over more quickly. But in general, one of our target audiences is the first-time programmer, but it could also be used for somebody who is an experienced programmer. The one thing that we discovered is that, or my own experience is that when I'm reading a technical book that has small chapters, I get a sense of accomplishment whenever I complete a chapter, and that feels good. It gives me a little endorphin burst, and that makes me want to continue working on it. Whereas if it's a big chapter, like those of you who have read my book, Thinking in Java, know that I have large chapters in there, and they're all pretty daunting. And they were daunting for me to write, because I felt like if I was going to cover a topic, I had to dive deeply and completely cover that topic. And so, as a result, each chapter ended up being rather large and intimidating. So we wanted to go the other direction with this. Instead, we wanted to, instead of dividing things up by topic, we wanted to break them down into individual concepts. And so each element is just talking about one concept, and it may not cover a whole topic. It may just, the idea is that it's just covering one little thing. The smallest possible amount of information that we could possibly come up with. So as a result of that, we thought they're not really chapters, they're atoms. So we decided to refer to these things, we sometimes call them chapters and sometimes call them atoms, and thus the name of the book is Atomic Scala, because we've broken it down into little pieces. And the idea is that we organize them so that all we're talking about is what you need to know for the next atom. And there aren't any chapter numbers, and that's because it was easier for us when we discovered, oh, this piece needs to go ahead of this piece. It's very easy to shift them around, and we've done that quite a bit. One of the differences with this book is that we initially thought that we would just do it as an ebook. So it is designed as an ebook first, and because my co-author hasn't published a book before, she wanted to have something physical, and people often still do. When I put out Thinking in Java, which was in 2000 roughly, I initially put it out as an ebook only. It was a free thing that you could download off of the web. I was one of the first people who did that. There's some argument about who was first. It doesn't really matter. But what I found at that point is that people decided that they wanted they wanted a print book for some reason, even though they could download the thing for free. So, we'll go ahead and do that with this one. But we want to make it, anyway, I had to do a number of things to make sure that it would work with ebook readers, which have a fair number of constraints to them, in particular font sizes and font types and widths, and we want to make sure that the code doesn't wrap. So you'll see, one of the things that you'll see in the code examples that I show you is that we tend to use a fairly tight formatting syntax. We cinch up space wherever possible, and that's because we wanted to fit it onto an ebook reader and allow people to expand the font size as much as possible before it starts wrapping. So for people who can't see as well, and I'm beginning to be one of those people, you may want to increase the font size, and you want the code to work. There's all kinds of issues around that with ebook readers. So you'll conveniently though, it turns out that by making it narrow, I was able to make a presentation like this much more easy. Okay, so first question a lot of people ask when we start talking about Scala is, do we really need another programming language? It seems like we've had so many of them already. I'm tired of learning new programming languages. Can't we just stop? And many people do just stop learning languages. I find that language design is an evolutionary process. And evolution works by doing lots of experiments and then selecting the ones that work better. So it turns out, this is just a little aside, because a lot of people talk about survival of the fittest. It turns out Charles Darwin never actually said that. He said natural selection. He never uttered the words survival of the fittest. So what we have here is many experiments, and then some of the best are selected, and then you have inheritance. So you have new languages take the best features of the previous languages. And that's what's happening with Scala, I think. Scala is, in many ways, it's what the Java language should have been. It's, as you'll see, there's a lot of things about it that are much cleaner, they make more sense, and most importantly, they do work for the programmer. But one of the biggest motivations behind Scala is the problem of parallelism, especially now that we are starting to see more and more cores in our CPUs. That's where things are going, is multiple processors, multiple cores within processors. And the problem of programming those is very daunting. And I know there may be people in the room who say, well, I can use threads. I get the same feeling from that as when somebody tells me that they are a good driver for a car. When someone tells me that they're a good driver, it makes me very nervous, because that's not the kind of thing that you want to be overconfident about. There's an effect. It's called the Dunning-Kruger effect. Some of you may have heard of this. You can look it up in Wikipedia. Dunning-Kruger means, what it is the less you know about a topic, the more confident you tend to be about your ability to be successful with that topic or your knowledge of that topic. So that has been my experience with concurrency and parallelism, which is something that I have studied for many years. And every time I think I understand it, I discover that, no, there's some huge part that I'm missing. And the more I learn about it, the more I understand that there's only a handful of people in the world who are good enough to write a program using threads and get it right. And those are the people who themselves say probably they won't get it right. So anytime you hear somebody say, oh, I can program with threads and get it right, be afraid. So the problem is we simply can't get it to work right using threading and shared memory. You have, well, one of the terms that people use is Heisenbugs, because it's the Heisenberg uncertainty principle applied to bugs. You will always discover these things. Whenever you try and observe those bugs, they will vanish, or they will become something else. So it becomes very difficult to track them down. And when you're doing parallel programming, the only thing that you can do is show that a parallel program is broken. You can't prove that it is working correctly. So what we really need to do is come up with a programming system so that we don't have to think about those things. Instead of starting with something that's broken, i.e. threads, and trying to work around the brokenness, what we need is something that is bulletproof from the beginning. So this is typically done by using separate memory spaces somehow, and then using communication. So communicating sequential processes is often what it's called. There's also some other interesting things which Scala, the ACA project that Scala is using, is experimenting with and developing. And one of the most interesting things about this is aspects of this is software transactional memory. And what happens with that is that you program kind of blithely, and the system, if it finds a collision, it backs up and tries it again, which is really a bizarre concept if you think about it. It's a little difficult to get your head around. The nice thing about it is that you're not thinking about the problem. The underlying system is. But it's very tricky to get right, so we'll see what happens with that. So one of the solutions is typically called the functional programming language, which many of you are familiar with. But many of the functional programming languages that we've seen so far are generally kind of strange and often restrictive. So many functional programming languages are functional only, and when you enter that world, that's the only thing that you can do. And very often that's a little too restrictive for solving the day-to-day problems. So some programming languages, Scala in particular, are using object functional hybrids. In other words, they're hybridizing object-oriented languages and functional languages so that you can do pure functional language programming if you want to, and if you don't, you can combine it with objects, or you can do non-functional programming if you want. One of the things that Scala produces is a much more succinct language, and in general, it appears that you get you write about half the amount of code that you would write in Java, and many people will argue that, well, Eclipse or IntelliJ will write all that extra Java code for me. But it seems that studies show that the amount of code, remember that code is read more than it is written, and the amount of code that you have to look at, the noise, really does impact what you're able to understand. So it does make a difference to be able to make a smaller amount of code. Scala runs on top of the JVM, and it is interoperable with Java, so that means that you can transparently call into Java's libraries, and it's also possible to call from Java into Scala. Scala is a statically typed language, and those of you who follow a lot of my writing know that I am not the hugest fan of statically typed languages, mostly because of the noise that is imposed upon you. Scala is really the first language that I've seen where the static typing really pays off in a lot of cases. And it also has type inference, so you don't have to cope with the static typing all the time. They're also doing some things that are you translating as we're going? Is that what's going on? Or okay, it's really distracting. So if you could just turn your phone off, that would be great. So it has type inference, which we'll look at. The syntax I find to be much more consistent and powerful, and the language in general has been fundamentally redesigned. Tomorrow, during my keynote, I will talk about some other more recent languages, in particular a language called Go, which has been developed within Google by some very smart people who have a long history in programming language design. Okay, so there are additional introductions here, and they've gotten the slides for this, and so I think they're going to be available. And these are actual links. So I've got several blog posts on Scala, and there's a couple of links to things that Martin Odersky, who is the creator of the Scala language, has. The first one is an actual video where he talks about interesting things in Scala. And in this one, he talks about shared memory concurrency and the problems with it. Notice that this third link here is asking whether Scala is only for computer scientists. So I'm not going to say necessarily that Scala is the be-all, end-all of all programming languages. It has, if those of you who have searched and read articles about it, you will probably have come across the kind of obtuseness. It's possible. Scala harkens back to the days of C++ when people would try and write the most obscure pieces of C++ possible. And that is unfortunate, especially at this point in its development, because the language can be very clear, and I think it's because we're in early days that people are tempted to write very obscure code with it. And anyway, that's the question that I'm asking here. I'm thinking, and I don't know the answer. I don't know if it's something that you really need to be a computer scientist to understand. We will see as time passes. So, some things I'll move through fairly quickly here. Comments are comments just like they are in Java, single-line comments and multi-line comments, C++ for that matter. One of the nice things that they've done with Scala is they have enabled scripting. So you can write code and compile it and run it in the usual way, like just the same way that you run Java code. But you can also create a script, and then from your command prompt, where'd my arrow go? Oh, don't have it. From the command prompt, you can say Scala and then the name of your file, and it will run it as a script without you having to compile it. We decided in the book that this would be the easiest way to teach the language to beginners and people who didn't want to have to mess around with the language too much to start experimenting with it. So most of the code, in fact, all but 3 files which we had to compile in order to get them to work. Most of the code is in script form. So it's fairly easy to use, and we'll show examples of how to run it from the scripting environment. It also has a command line interpreter the same way that Python has one. When you start up Python, you get something and you can type to it. It's called the REPL, for read, evaluate, print loop. One of the things that you'll notice here is that in Scala, you don't have to say system.out.println. You can simply say println here, because it has a package of pre-definitions that come in whenever you run Scala, and it takes care of things like namespaces in the case of println. So they do, that's just one of the many things that they do. Okay, so let's take a look at values and data types and initialization. The way that we create a value, now I'm going to start with values. There are also variables. So a value is something that you assign to and can't be changed after you assign to it. This is part of the functional programming of Scala. And it's important in functional programming to try never to change anything, to create a value rather than a variable, because it makes parallelism a lot easier if you never have to worry about things being changed. So we prefer values to variables, and at first it seems kind of strange. If you're not used to it, it's a weird idea, because you're going, well, I'm so used to taking something and then changing it. But it's surprising how quickly you can get used to it. The other thing that people have trouble with sometimes is they're thinking in terms of efficiency. And I don't know if you've heard the, I think it's Knuth or I think it was Knuth who said premature optimization is the root of all evil. And I have known this forever, and yet my brain constantly goes back to thinking about how efficient something is, even though every time I've done it, I've been wrong. Every time I have made any assumptions about efficiency, I've been wrong. So very often using vals instead of vars is more efficient. So what we do is we say val, we give the identifier for the variable, a colon, and the type. And this pattern is very consistent throughout the language, including for the return value types of functions. So here we see val name, colon type, equals initialization. And as I pointed out, we use a very tight format, and so often people will put a space between the colon and the type. We're not, because we have these space constraints. So now let's look at an example. I'm feeling pretty good about myself because I spent a lot of time designing the slides for this, because the slides come directly out of the book, so that I could dynamically change the size of the font. You can see I'm doing that here. That's all JavaScript stuff that I built in, but I discovered that when I plugged it in here, I needed to change the font size. So here's an example of a val called whole. It's of type int, and it's equal to 11. It looks like I've forgotten the semicolon. But the reason is that that's one of the things that immediately made me like this language, is that the designer said, well, you know, the semicolons are extra noise. We don't need them. Sometimes you can still use semicolons if you want to put things on the same line, but we don't need them, so let's leave them off if they're not necessary. So the parser has to work harder, but in my opinion, that's what a programming language should do. It should work harder, so we don't. So no semicolons unless absolutely necessary. It's got doubles, so my identifier here is fractional. Booleans, strings are built-in types, and it has single quoted values, and this comes right from Python, the triple quoted values, which allow you to have multiple lines within a string. So that's a very nice thing. Over here on the left, I've got line numbers in blue, so those are just for the book, and so that if you want to ask a question, you can say on line 8, etc. So that's, but other than that, they're not part of the code itself. And so I can print the values, and the outputs here you can see are the various results that you would expect. All right, so, oops. All right. Variables, it's exactly the same, except we use the keyword var instead of val. And it becomes kind of a game when you feel like you have to use a var instead of a val to try and figure out how not to. So it's an interesting little puzzle challenge. And the language seems to have enough features in it so that you can always use a val instead of a var. And sometimes it's just awkward or inconvenient, or you just don't want to for some reason. But it seems like if you spend a little time puzzling it out, you can always use a val. All right, type inference is what it will do is, notice here I say val n, but I don't give a colon and the type. So what Scala will do is it will figure this out based on in this case, based on the value that I'm assigning to it, the initialization value. So notice because there's a 0.2 involved, it identifies it as a double. Now, what I'm showing you here is the REPL, and we should look at, let me bring this up here. So, make that a little bigger. So to start the REPL, once you have Scala installed, you can just type Scala with no arguments, and it will start the REPL. And sometimes it takes a second, and you can see here we are version 2.9.1. 2.10 is on its way, and it'll probably come out before we're done with the book, so we'll just update it to 2.10. So you get the Scala prompt here, and if I put in val n equals 1 plus 1.2, you'll see what happens. Val n. Okay, so this is going to dynamically evaluate this, and it's going to, so it tells me what n is, and notice it's decided that it's a double. So that's the type inference. In general, you can treat type inference as something that the language will do if it can. It will try and figure out the correct types. And if it can't, then it will give you an error message. But much of the time it can. What we do initially with the book is, so as not to throw too many things at you at once, we tend to use explicit typing until we reach a certain point in the book, and then we decide to, okay, now that you understand enough about the basics of the language, we'll look at some of the fancier things that you can do with it, including writing more succinct code using, for example, type inference. But we'll start out by being explicit. But keep in mind that many of the examples that I'm showing you, you'll be able to use type inference and not, you won't necessarily have to say everything. Okay, so one of the places that Scala is consistent is in value or expressions. Basically, everything in the language is an expression. And I had forgotten some of my foundations and had to go back, or maybe never learned it properly in the first place. That's more likely. So I had to go back and really figure out, all right, what is a statement versus an expression? And how does it work in Scala? So a statement is something that typically does not return anything. It is called for its side effects. Thus, you can remember it as a mnemonic, as a statement changes the state of your system. Whereas an expression, like when you squeeze juice from an orange, you're expressing the juice out of that orange. So an expression produces a result. So that's the difference. A statement doesn't produce a result, an expression does. And to be more consistent, virtually everything in Scala is an expression rather than a statement. And that makes things I find it makes them easier to think about. So if we look at, so here are, well, actually these are expressions as well, but say I plus j is an expression, produces a value. We can also create a compound expression here where I've surrounded it with curly braces. And with a compound expression, you can put other expressions inside of a compound expression, and the last expression in the compound expression becomes the result of that expression. So here I can do all sorts of calculations, and the value that is assigned to A2 is the result of this final expression here. I1 plus J1. And this is interesting because it's also consistent when you're dealing with functions. You don't have to use the return keyword when you're working with functions. You simply put a final expression there, and that becomes the value that's returned by the function. So the consistency is actually quite nice. So if we print A2, oh, this is interesting. Yeah. I think somebody changed this and didn't run the tests. Okay. Yeah, well, you'll see the problem with this, of course, is that there's no testing framework in place yet. But we thought of that, but we weren't ready to explain it to the beginner at this point. So so this should be A2 rather than ATOO. So all right. Now, what about an expression that does not produce a value, like print line 5? What is the result of that expression? If we type that into the REPL, you'll see that it gives us this thing called unit. Unit is basically the equivalent of void. The idea is that every expression produces a value, and so one of those values can be the unit value, which means nothing. And it can also be expressed by empty parentheses. Okay. Conditional expressions, these are fairly consistent with things that you've seen before, or at least fairly obvious. So I can say if some kind of conditional, and then in curly braces, it turns out that I don't have to use the curly braces for a single line expression like this, but we're going to be consistent and put everything inside of curly braces just so that we don't throw too much at the new user. So you see the result of that. Here's another one. So here I'm using an expression to initialize a Boolean. And again, I wouldn't have to have the curly braces on this. It'll allow me to get away with all sorts of variations, but we want to be consistent. And so I initialize the Boolean and then put it inside of the if expression. Here's another Boolean. So it has the not, just like in Java. There's an else, so you can say if and else. And instead of having a ternary expression, we can just say if, and then this, or else that, and that becomes the value that we assign to result. So it eliminates that extra syntax that we've had in other languages, the colon, the question mark colon that's often shows up. Well, if we don't need that, then no reason to add it and make more noise. All right, let's look at, okay, so for loops. For loops are also fairly similar, except that with a for loop, the idea of iteration is built in. So instead of the more primitive, if you think about where C++ came from, which is from C, and C was designed to be a high-level assembly language. So you're pretty much expressing everything, but the idea of C was to be transparent across machines, whereas assembly language you had to write for the particular machine. So it was kind of silly to hang on to that low-level detail for as long as we did, the actual talking about how to step through things. So with Scala, this is more like the way Python does things. For I, I think there's supposed to be an arrow here. Yeah, this is disturbing. Well, this is why it's so good to give presentations. So I think this is supposed to look like this. My question is, how did it slip through our compilation system? Anyway, so this is actually intending to say that this goes through the range I goes from 0 to 10. And if we look down here, we'll see that. Notice it goes 0 through 9, so it does not include 10. So again, it's a little bit more succinct than the usual thing that we have to do. Also note that I here is using type inference. It's figuring out what type I is supposed to be. I don't have to say, it turns out it's actually using vals, not vars, but we don't have to think about any of that stuff. It's taken care of for us by the language. And it's also figuring out what the type is. We can also use something called range. This is an object that is part of the predefined elements when you run Scala, and range basically does the same thing. You can see, again, we get 0 through 9. Okay, and range can also be given a step value. So 0 to 20, step 2, you can see 0, 2, 4, 6, 18. And then here I'm going to use a var because, well, initially I want to create a sum. It turns out there's a way to do this without using a var, but we'll just keep it simple for now. Let's start with a var. So we're going to go through this range and print this out, and then you've got the plus equal, which should be familiar to everybody. And we sum it up, and you can see here we're doing the sums as we go, and finally we print out what the sum is. All right, so for loops, the basic for loop is fairly consistent with things that you've seen before. So let's look at objects, which are, I'd say, better integrated into the language than they are in Java. And so this range that I just talked about, let's make one of those. Okay. So it tells me what this range is, and echoes back to me everything that it is. Notice that it's talking about, it gives you the full path to what that thing is. Normally don't have to think about that. Now what I wanted to show you though, which is interesting, is now I'm inside this REPL, this read, evaluate, print loop, and one of the things that it has built into it is if you hit tab, it gives you all the possible completions. And notice that this range object has a lot of stuff in it, including things that we can't hope to understand at this point. Flatten and fold right and generic builder and stuff I'm not sure what does yet. But it gives you the impression that we have a significant class hierarchy here, and the objects have a lot of operations you can perform on them. But let's do something simple, like let's say sum, and I did a completion here. We're able to see that? Yeah, okay, good. Now if I do r.sum, it actually sums up the values. So it's kind of a nice thing to have built in there. Let's see. See if there's something else that might be interesting. Add string. Well, let's see. Maybe collect. I'm not sure what collect does. Yes, so collect. And it'll probably say something like, okay, missing arguments. So it tells you, yeah, it requires maybe a function or something to use collect. So how about to map? See if that probably won't work either. Yeah, cannot prove that. That's interesting. It's trying to do some kind of mathematical proof here before it will accept my to map. Anyway, there's a lot of operations that are available with most of the objects that are built into the language. All right. Scala doc is, see if we can go here. Oh, okay. The web isn't working. Otherwise, I would show you Scala doc. And okay, get rid of that. Go back here. So the Scala doc is, you can either get it online or it can be part of, I mean, it comes whenever you install Scala on your system. And it's quite thorough and kind of follows the foundations that were set by JavaDoc and has improved it in places. So it's helpful. We talk about that in the book. We don't really need it for this seminar other than just you should know that it exists and that it's pretty helpful. And it works. There's a Scala doc compiler just like there's a JavaDoc compiler, so it follows all of that. Okay, let's take a look at one of the one of the objects that's built into the language, which is vectors. And we're going to use this a lot. Even though you probably remember that vectors in Java turned out to be a really bad design, and so people started saying just don't use them, and then after a while they said, oh, well, we fixed them and you can use them again. And anyway, it was quite a mess. It was because Java was rushed to market because somebody imagined that there was this window of opportunity that if they didn't meet, then people would not use Java for applets on the internet. So fortunately, they rushed it out, and now we use Java for applets on the internet all the time. Okay, good. Somebody's awake there. All right, so a vector simply holds other objects, and one of the nice things that you can do is you can use type inference here. And a little while later, we will see that there's a much nicer way to use parameterized types in Scala. Okay, seriously, dude. The phone, it's just, yeah. Okay, yeah, maybe that's why. Anyway, it's just like really annoying. Okay. So I can simply throw objects into the vector and it'll figure out what type of objects that it holds. Okay, here's something which is a little strange at first. To index into a vector, you don't use square brackets. Square brackets are used for parameterized types. So what instead you do is you use parens. Scala uses, it's not really operator overloading. It's just that everything can be redefined. So it's a little bit different than what we would normally think of as operator overloading. I should probably take a step back. And so for those of you who are still dealing with the way that operator overloading was left out of Java, and why? Because James Gosling said, oh, operator overloading is bad. The reason that he said that was really a misunderstanding. He didn't really understand operator overloading well enough to know whether to put it in the language or not. I spent a lot of time with C++ explaining how to do operator overloading, and in C++, operator overloading is very difficult to get right because C++ doesn't have a garbage collector. If you have a garbage collector, operator overloading becomes quite easy. Python has a garbage collector, and doing operator overloading there is trivial. There's nothing you have to worry about. Without a garbage collector, like in C++, it was very difficult to get right. So as a result, just kind of as a knee-jerk reaction, Gosling said, oh, well, operator overloading is bad, so we won't put it in Java, even though with the garbage collector, he could have put it in Java and it would have worked quite well. So in Scala, they said, all right, let's set it up so that you can redefine pretty much everything. But for simplicity's sake, the parens are used for indexing, and well, anyway, I found it surprisingly easy to get used to, just simply using parens to index into it. So it takes a little bit of adjustment at first, but I didn't find it to be that much of a problem. All right, so here again, if what we've done, we filled a vector up with elements, now we can take each element of the vector using this arrow, which it turns out is just another kind of symbol. It's a function. One of the things that Scala allows you to do is use not only the function call syntax, but a natural kind of syntax. So this is simply calling a function. It just allows you to, instead of having to use parens to call the function, you can just put the thing in there with spaces around it. We'll see an example of that shortly in the next section. So I'm getting each one of the elements from V1 and printing it out. Here is another vector. Now this one is holding doubles, and notice that I can call reverse. That was another one of the things that I had with my, let's see. So my range R was this, and I could say R dot reverse, like that, and I get the elements backwards. So there are certain functions that are built into all types. It's an object-oriented language. All right. And then here's another vector that's holding strings. And again, we're using type inference again. And this one, I can sort them if it's possible to sort them. It tells me, it figures out at compile time whether it can be sorted or not. I can do things like get the head and the tail, and we could see the result of these things. So. Okay, so now, oh, I think I'm out of those slides. Oh, okay. So let's take a look at slightly more complex compound expressions, just to emphasize what a compound expression is. So I'm going to initialize a val using a whole bunch of stuff inside of curly braces. And notice that I define some other vals. I can do a print statement inside of this compound expression. It's just a collection of expressions. a compound expression is just a collection of other expressions. And at the end here, I've got an if expression which produces true or false. And since this is the last expression in my compound expression, the result of is open will be either true or false. And therefore, the type inference will figure out that this is a Boolean because it's going to get a true or a false at the end. All right, so there's one compound expression. You can see it prints something out, and the result, actually I should be printing out what the result is as well. Okay, here's some more compound expressions. Got a string and an hour. So again, type inference infers that this is a string and this is an int. And then I've got an if expression here, which says if this is equivalent to swimming or, so most of this stuff is going to be familiar to the Java programmer. We define some other values, print statement, and then here's my true and false. And notice that's one possible result of this, and another possible result is just returning true. All right, so it's just another kind of expression. All right, so now we're far enough along that we can deal with the problem of testing. And one of the things that I have struggled with, starting with thinking in C++, is I had a problem, which is every time I would go into a bookstore and pick up a programming book, I could pretty much open it anywhere and find some bug in the code, like we've been seeing one or two places here. So that seems to me like it makes things harder for the person who's learning the language if they can't trust whether things are buggy or not. So I would find bugs in the code, and I thought, well, I don't want to do that in my book. How can I make sure that doesn't happen? And initially, with thinking in C++, what I did was I said, well, I want to be able to at least make sure that the code compiles, because people weren't doing that. My assumption was that once I demonstrated how to do this, all other book authors would say, well, of course, we want to make sure that our code compiles in our book. And it would change everything. It didn't. There was only a few people who started doing that. And most of those people had already been doing it. They had figured it out themselves. So in this book, we wanted to not only introduce the idea of testing early, but we wanted to make sure that people would begin understanding the value of testing right from the beginning. Because what's happening now is people learn to program with the language, and then later they start thinking about, for example, test-first coding, or at least building tests into your system. So we wanted to start people very early. Now, the system that we created is called Atomic Test, which is kind of fun because it sounds like you're blowing up a bomb someplace. And also the cover for the book will look like mid-century modern with things like, well, so this is all the stuff from the 50s with the cars with the fins and the rocket ship, the Sputniks and all that kind of stuff. So it should make for an interesting cover design. Anyway, this is where the syntax power of Scala came in handy, because we didn't want to overwhelm people. One of the things that I've had trouble with a lot of the testing frameworks is that they've been excessively noisy. The amount of code that you have to write in order to do tests is often more code than you're testing. So I wanted it to be very simple, and we struggled around, and this was one of our first interesting learning experiences, and we came up with this test system, which, as you'll see, is very simple. What we have to do is import our test library, and the underscore here means everything. Underscore is used possibly a little bit too much inside of Scala, but in general it means either everything or some fill in the blank. I suppose that's why it was an underscore. It's the blank. So in this case, when you put it inside of an import statement and you say dot underscore, it just means everything that's in that package. All right, so we've got the vectors like we looked at before. Here's something a little different. Vectors have a union method, so I can unionize the two vectors. Now, so in this, I do the normal method call that you've seen before. I say v1 dot method name and give it the arguments. Now this, quote, natural syntax that we have that's allowed by Scala is the same. They didn't have to change the functions at all in order to do this. So this is the same function that's being called, but instead of saying v1 dot union with the argument list, I can say v1 union v2 with just spaces. Okay, and that's built into the language. And once you write the union method, you can use it this way. Well, it's been written for you already. All right, so what we wanted to do is take advantage of that in our testing framework. So there's also an intersect method that's built in, and we can use the alternative syntax there. Now, we wanted to include that for our test framework, and we wanted to make the test framework as simple as possible. It doesn't cover all the bases. All we wanted to do was test the code in the book and make it something that's simple enough that it doesn't overwhelm the reader. So what we did is we defined the is method, and because of the built-in natural syntax, we could just go ahead and say, for example, v1 is, and one way we can do it is with the quotes, but in this case, we wouldn't have to use the quotes either. It would figure it out either way. So what this will do when this script is run is it will print out a result from this expression. And it will also perform the test. It will make sure that v1 actually is, well, it does a string conversion on it in this case because it sees a string over here. But if it was just the vector, it would simply do a comparison to the vector. In other words, if I didn't put the quotes on here, it would simply do the comparison. The code for the test framework is in the back of the book, but we don't explain it. It's more complicated than is intended for our readers to understand. It's got some tricky stuff in it that we had to figure out. But the result is very simple and transparent. So if we, for example, select element 4, we can say v1 of 4 is 11, and it will test that for us. So from now on through the rest of the book, we can put these expressions in, and it will test for us. And also we can use this to write test-first code for the exercises, which we do. There's a string builder. Also notice that, well, there's a new... I'm hoping that we've introduced new at this point, but I'm now wondering if we have. Anyway, there is a new keyword to create new objects, but notice that I don't have to put parens in. I could say new string builder, empty parens if I wanted to, but Scala is minimalist in this way, and so if you don't need parens, it doesn't force you to put them in. It figures it out. Another just nice little convenience for us. So I can call the append method and build my string, and then I can use the is for that as well. Create a vector, say what its reverse is, and then notice that in this case I'm using quotes, and in that case it sees that and it converts it to a string. And in this case, I'm not using quotes, and it notices that, and it simply compares the objects directly, compares v3 reverse to this vector. So it works both ways, with strings, or with a string conversion or without. And then notice that the compiler will, it's fairly clever. It will parse through this, even though in the book we've had to break things up into multiple lines because we can't fit everything into the width. And notice that it figures it out. It goes, oh, well, the expression must not be done yet. So I'll look, and basically I'm creating the expression, and I have to build it with the plus sign. And it goes ahead and compares that, looks at the head, looks at the tail, and the whole thing. And then here's an example just to see what happens when we compare things that are unsuccessful. So foo is bar will produce an error message. So what it does is it prints the thing on the left of the is sign. So we know that we get some output. That's the intention. We wanted the reader to get some feedback, even though in a normal test framework, you wouldn't give feedback unless something was broken or for some other reason you needed to. We wanted the reader to get feedback, so it's always printing that out. And all of these things happen. Now down here, it says, oh, there's an error. So it says, okay, it prints out the value. It says error expected this. So it tells you what it expects. And that's it. That's the whole test framework. And the whole thing fits on, it's not very long. It's a little dense, the code, but you don't have to look at it. So it's not important to look at if you don't want to. Yes? Yeah, I mean, my preference would be to compare a vector to a vector. I was just making a point there saying, okay, you could do it as a string or you could do it as the, as the vector itself. My preference would be to always compare a vector to a vector. Well, we wrote the framework so that if it sees a string on the right-hand side, it takes the left-hand side and converts it to a string so that it'll work. But most of the time, if it doesn't have to be a string, it's probably better not to. Yeah, but no, I agree with you. I don't think it's as clear that way. Okay, so you'll notice that in the rest of the examples we do include atomic test so that we can do the tests. So this is how you define a function. Okay, I'm taking slight liberties here. Those of you who have seen Scala realize that, okay, I'm actually creating a method on the global object. But in the scripting that we're demonstrating here, we can pretend that it's a function and get away with it. We do take some liberties in the book in order to simplify the understanding, and then later on we can say, okay, we lied just a little bit about what that was, but it was easier for you to understand at that point. So I'm calling this a function, and we use the def keyword, the function identifier, the argument list, which you can see here is just a single argument, and the argument list follows the same pattern as we've seen for vars and vals. You give the identifier for the argument, a colon, and the type, and then after the close paren, we have another colon, and we give the return type of this function. Okay, so that is all of this is the function signature, and the function body begins with an equal sign. So here we're saying, okay, this function signature thing equals, and then we give the body, which interestingly enough is simply an expression. So it's some expressions within curly braces, and then the final value is produced. So it's an interesting, different way to think about a function. A function is an expression that has some substitution involved. In other words, you take whatever's in the argument list and you substitute it inside of this expression. But other than that, it's just another expression. And it's kind of helpful to think about it that way, because when you start thinking of everything in terms of expressions, a lot of things seem to, at least for me, they seem to become clearer. And it also emphasizes the consistency in the language. For example, just the last expression within the compound expression is the result that is returned by this. Okay, when we call the function, that looks like all of the other function calls that you've seen. You can take the result and assign it to something. In this case, again, it's using type inference. And then if I say R is 10, my test code will run, and it'll verify that my code hasn't broken for some reason. All right, so that's the basic idea of a function, how you define one. All right, so here's a slightly more complex function. It has 3 arguments, x, y, and s. It returns a double, and it prints this thing. It takes x and y and multiplies it by 2.1. All right. And then you could see it being called here. Pretty much what you'd expect. And notice the consistency when we define the variables, the arguments, we say colon and their type, and the function itself, we say colon and the type. So it's quite consistent across everything, and I find that to be helpful. All right, here's an example of a function that doesn't return anything. Now, I will point out to you that, again, we're being more explicit here. We're specifying the return values, but type inference would allow us to leave those off. But we want to be explicit here. So the println function doesn't return anything, and therefore the result of this is unit, which can be expressed as the empty parens. This is one of the nice things about the test framework, is that now, in a sense, we're able to make these assertions within the code, and you know that if the script executes properly, then that assertion is true, and you can see it in the code rather than me having to explain it separately. So it's coming out quite nice. All right. This one takes a Boolean argument. It returns a string. Now, here's a place where return is necessary. If you have to return in the middle of the function, the return keyword is still necessary. You could use the return keyword at the end, but my approach is never to use something that I don't have to, because I think it adds noise to it. So the return keyword is explicitly for returning from the middle of a function. People have many arguments about whether that's a good thing to do or not. I think it's useful sometimes. Other times, maybe you want to avoid it. It just depends. If you have a function that is so big that it's confusing to return from the middle of it, maybe you need to make a smaller function instead. All right. Okay, so alternatively, this becomes there's only one expression within this function body. And so in this case, this expression is returning true or it's false. And so I don't need the return expression. I don't need the return keyword. Okay, here's another function which has some Booleans, and this is basically to show some of the Boolean operators, the ones that you're probably familiar with, I assume. The double ampersand, the nots, the ors, double equals for equivalence, greater than, equal to. All right. Here's an example of using basically the ternary operation. It's not an operator. So if arg 42, else 47, once again, this is an expression, and whatever it results in, 42 or 47, becomes the result of this entire expression. And since this expression is the last expression in the function definition, it becomes the result of the function. So if we pass it true, we get 42. If we pass false, we get 47. All right, let's look at one of the more interesting features of the Scala language, which is pattern matching. Pattern matching is a much fancier version of the case statement. If you've been following Java, you know that they added strings to the switch statement, which is really kind of weak. It's a small nod because most of the pressure came from C#, because they had a slightly more complex way of doing switch statements. They could compare strings. So Java had to compare strings as well. Well, if you think about the general issue, is that you want to do a switch on anything. And so Scala allows you to do that. And it does this with what's called pattern matching. And what you do is pattern matching is enabled using the match keyword. So in this case, I've got a function, match color, takes an argument, which is a string, and then it takes that, and it calls match, and then you have a sequence of cases against which it's going to match. So if I pass it lowercase red, it's going to return uppercase red, blue, green, etc. And then finally, here's our friend, the underscore again. And the underscore is kind of, I'm sort of liking the idea of calling it fill in the blank. Looking for my, well, okay. So this will match these three things, but if it doesn't match any of those, it will go to this default case. And you don't have to put an underscore in there if you don't want to. And that'll work fine as long as Scala never has the possibility of encountering anything else. But it will check that. And very often, I think that it will do it statically, but I'm not quite sure about that. So that's the basic idea of pattern matching, and we'll see some more complex examples of that shortly. So I can say match color white is, it's an unknown, and this produces blue. So once you see this, it kind of spoils you, because the ordinary case statement, especially when you think about it a little bit, you have to, well, at least up until the case of dealing with strings, we've always had to match against an integral value, which seems very primitive and kind of assembly language-like, which it is. Again, we're hearkening back to C, which is a high-level assembly language, and it was way better to do it that way, to have a switch statement in C than having to code it in assembly language. But still, so many of the constructs that we're still stuck with in C++ and Java are throwbacks to that those primitive days of having to do everything explicitly. So this is much more useful. It's not only easier to solve your problem, it's a lot easier to read it. Okay. Now, because pattern matching is so, such a useful thing to be able to do, they actually introduce a specific type of class called the case class. We're introducing the case class is our first version of the class because it's simpler for the reader to understand. A case class is a very minimal thing. So when you put the case keyword in front of your class definition, it automatically takes, so I'm defining a class called dog, it automatically takes this name argument or any of the arguments that you put in them, and it turns those into fields inside of the class. So it does all that work for you. And this is the entire definition of the case class. I've defined the whole thing there. And it's defined the fields. It takes whatever you pass in as an argument and it assigns it to the internal field, and you can reach in and read it. It automatically turns them into vals rather than vars. So now that I've defined that, I can say, well, and it does something else for me, which is that it obviates the need for the new keyword. So instead of having to say new dog, etc., with the case class, that's taken care of for you. That's a little trick that you can do yourself with non-case classes, but it's not really important at this point. It's made it simple. What's interesting is this is exactly the syntax that Python uses for all of its classes. You don't need the new keyword if you think about it. That's, again, an artifact of C++ that we inherited kind of mindlessly into Java. And here, he still does have a new keyword. Odersky still added a new keyword. But we can get rid of that if we want to. I don't know. Personally, I think that's a little bit confusing. I think that he could have made it consistent that way. And so I'm not exactly sure why he chose to have both ways. But in any event, for simplicity, you can do it this way. So I'm creating a dog called Henry and one called Cleo. And then I can create a vector of dogs. And notice that type inference figures out, even though this is a brand new class, it figures out what that is and constructs the vector to hold my dogs. And then here's what that vector looks like. Notice that it remembers what the structure of that dog is, including what's inside of it. So that's kind of interesting. I can create a case class called cat with a name and an age, so 2 arguments. And again, both of those automatically become fields. Name and age become fields within the cat class. All right. Let's take a look at Scala's parameterized types. We've looked at vector a little bit. There are other collections, of course. Scala's collections are quite rich. But again, we're trying to keep everything simple, so we're just going to stick to vector. So here, the type is inferred for both a vector of ints and a vector of strings, but I can also explicitly type it. So here I say, instead of just val v1 equals vector, I say val p1 colon, so I'm going to give it the type, and then I say vector of int. So here's where the square brackets are used. Place the int there, and it's exactly the same on the right-hand side. I have simply explicitly typed it rather than using type inference, and the same with a vector of string. So that's how you specify what the type is for, what the type parameter or parameters are for something that is parameterized. Much more straightforward both to create parameterized types and, more importantly, to use them. One of the problems that happened, and you can see here's a situation where Scala is significantly a significant improvement over Java. One of the mistakes that they made in Java's type inference, and you know that if you read, well, the 4th edition of Thinking in Java, you notice I put in quite a number of complaints about the problems of parameterized types in Java. The real problem is that the user of the parameterized types has to know a lot about them. You still have, in Scala, you still have where the type parameter has to be inherited from or inherits from, what is that called? What's that? Covariance, and somebody hand him this cup. Okay. I'm not going to be able to get rid of these things, am I? They handed these things to me at the last minute and say, here. Okay, yes. Contravariance and covariance. It still has those, which I'm frustrated with parameterized types in general because even though, C++ is so bad and everything, its parameterized type mechanism was so much cleaner than anything that we've seen because of the way that it was structured. It worked a lot better. Yes, initially there were problems with the error messages that came from parameterized types, but everything else was much cleaner. For example, you didn't have to worry about covariance and contravariance because it uses structural typing rather than the stuff that we use here. But anyway, it's still much simpler, I think, than it is in Java. So a lot more straightforward, and in particular, it's much more straightforward for the user, the consumer, and that's an important thing. When you have complexity, it's ideal if the complexity can be pushed towards the side of the library creator and not towards the library consumer, because it makes it more difficult for people to program if it's on the consumer side. Okay, so return types can also be parameterized. Here is an inferred return type. Notice that I don't have the colon and the return type. It figures it out because, well, it's returning a vector of char, so it understands that it needs a vector of char, and it does it for you. But you can also be explicit about it. You can say, I'm returning a vector of char here. I prefer to use type inference unless something demands that I be explicit. I like to be smaller and simpler if I can get away with it. And you can see that we produce exactly the same result using the is directive. Okay, so as a little taste of functional programming, I'll introduce the for each construct. So we've got a vector of strings, and I can do the thing that I've done before with the for loop. For color gets each element in colors, print it. But the vector and pretty much all of the collections have a for each operation as well. Boy, I'm seeing all kinds of things. This is the advantage that I had when doing both thinking in C++ and thinking in Java, is that they began as seminars, and every time I gave it, I had to really focus on each of the examples, and I would always see things coming up. Like, for example, here we're introducing the idea of an anonymous function, and we haven't really introduced anonymous functions yet. So this is the wrong place for this particular atom. This needs to be moved forward, or anonymous functions need to be brought back. Okay, so here is, anyway, for each, what for each does is it takes each element in the collection, and in this case is a vector, takes each element and it applies this function to it. Okay. This doesn't look like a function. Why is this a function? It's a function because of this in Scala they refer to this as a rocket because it looks like a little right-hand rocket. It's got the little lines. Okay, it's obviously an equal sign and a greater sign. Okay, and what the rocket does is it's actually defining an anonymous function. On the left-hand side, you have the argument list. If in this case, we only have one argument. We don't have to put it in. We don't have to surround the argument list with parentheses. So there's another one of these little shortcuts. Yeah, I can see this is a problem because our goal was not to overwhelm the reader with too many things all at once, and that's exactly what this particular example is doing. So anyway, so our argument is this one element color, and on the right-hand side, we have the code that is executed for that function. And in this case, it simply prints it. And so, as you can see, well, what we're doing here is we're going through and we're taking red, green, blue, gray, white, and we're printing each one of them. All right, so this is a more succinct way of doing it. Notice the difference between our for loop and the for each, which is a functional way of doing it. All right, certainly I could just write a for loop. I could be explicit about stepping through this. And for each only gains you a tiny benefit. But remember all of the for loops that you've written where you've made mistakes. You've made various different types of mistakes. This eliminates that. This says, all right, well, we'll just remove that little problem that you often have when you write a for loop, and we'll make it into this function which will take care of that. Little tiny step, but with functional programming, you have a bunch of those little tiny steps, each of which gives you a little bit of a benefit, and you start combining those, and in each case, you, like for example, in this case, you don't make the mistake of that you might make with a for loop. That little thing is eliminated for you. All those little things are kind of taken away, and the result is significant benefit. But it's not always as obvious when you first see it. You just go, I can write a for loop. It's the subtler aspect of it. The other thing about functional programming is you're able to combine these functions in a fairly straightforward fashion. So instead of writing explicit code, you simply combine functions, and there are clever ways to do that. Now, we're not going into that in this volume. We're talking about writing a second volume which will introduce functional programming, but we're only just touching on it here. Okay, so here's anonymous functions. Probably needs to be moved back before what I just showed you. So this part is the anonymous function. Notice in this case, I put the parens around the A. So there's my argument list. Here's the rocket, which is pointing to the function body, which could be, in this case, I don't have any curly braces around it, but I could also have curly braces, and I could have a compound body if I wanted to. Very often you keep it very simple, and you just have maybe a single expression as we do here. And the result of this is a function definition, which I can turn around and assign to fun1 as, and notice what I'm doing here is I'm using a val. And I do val here as well. I can also say def if I want to. The difference is kind of too subtle to talk about here. But the basic idea is that, well, this variable is being assigned to something. And that something doesn't have to be your typical type, int, float, string, long, double, etc. It can actually be a function body. And that's an important thing in a functional language, is to be able to manipulate functions as if they're data, basically. And you can pass them around. You can pass them into other functions. You can compose. You can create functions by combining other functions. So that's kind of a powerful thing to be able to do. And that's one of the cores of functional programming. So being able to take this anonymous function and assign it to some identifier is an important part of functional programming. Here I call it, and it looks just like any other function. Here's something with 2 arguments. Just add another argument. So it's all in the rocket, which is the anonymous function definition. Here we go. It's anonymous here up until the point that I assign it to this. But if I wanted to, I can take this part and I can pass it, for example, into another function. All right. All right, let's look at the for expression, which is more sophisticated than the for loop. And in this first example, I'm going to look for, well, what I'm actually doing here is I'm looking for everything, all of the ints that are even and that are greater than 5. We had to abbreviate it once again to meet our width constraints here. And the argument is a vector of int, so I'm receiving a vector of int, and I'm producing a vector of int as a result. Now, in this case, initially, in my first cut at this, I'm saying, well, I need to be able to reassign the result to other things. So I'm going to have to make it a var, because I have to stick things into it. So it's got to be a var, apparently. All right, so my var result is a vector of int. And let's see, I have to put the parens here to create that vector. So this is instead of saying new. Now what's occurring to me here is I wonder if I could simply say new vector of int without the parens. Actually, let's try that. See if it likes that. No, it doesn't like that. I think it probably doesn't even like the new. No, it doesn't like the new. Let's see if I can say vector of int. Nope. I have to do this. Yep. Yep, that's the only way to do it. Okay. All right, so I've created a vector of int, and now I'm going to go through my v, which is my argument. I'm going to take each element out of v, and I'm going to say if n is greater than 5 and n% 2 is 0, which means it's even, then, so notice that this, if you're familiar with the idea of a comprehension, especially if you've worked with Python. Python added comprehensions maybe 5 years ago, something like that. Very powerful concept, so that instead of having to do all of this piecemeal, I can do it in this single expression. I can say every n in v, if n is greater than 5 and n% 2 is equivalent to 0, add that to my result. Append it, basically. So what I'm doing here is, this is, well, you can call it an overloaded operator if you wanted to. It's a symbol that they created, this colon plus. And this means to append n to result. And we can see here is this vector that we've created. And you can see, okay, each of these is greater than 5, and each one of them is even. So if I pass it through that, we get this result. All right, so what I do here is I build this result vector, and then I return it as the last element in my function. All right, well, in Scala, we don't like being forced to use vars, so there is a keyword called yield, which does a little bit of magic for us. And we're able to say, all right, let's create this result for expression just as I had before. Every n in v, if n is, in this case, if n is greater than 10 and n% 2 is not equal to 0. Yes? Yes.
Thank you very much. In this slide, you said that it's appending result equals result colon plus n.
Yes.
But isn't it rather concatenating like in strings? Is appending in the meaning that we are adding to the vector, or we are creating new vector? For example, if you are doing the same.
Yes, good point. Yes, thank you. Okay, so the question was, yeah, I was sloppy when I described this here. What I'm doing here is I'm taking result. This is saying, actually, it's saying create a new result object by taking the existing result and appending the n to it, and then turning around and reassigning it to results. So I could have assigned it to something else. The reason I had to use var was so that I could assign this to result again and build it up. But yeah, you're right. I'm actually creating a new vector in each case. Thank you. All right. Okay. Scala allows us to, by using the yield keyword, it does a nice little trick for us. So notice here, result is now a val. So it's not being changed. My expression, my for expression is the same, but now it's saying yield n. And what that is doing is essentially building the result for us without us having to do that reassignment every time. It's basically collecting all the values of n. Now, it knows because, well, here I've done type inference, but it also knows that, well, I'm getting a vector of, I'm taking it out of a vector of int. So even if I didn't use type inference, it would figure out that result would be a vector of int as well, because of where it's coming from. But the yield keyword is basically collecting all those things for us. In fact, we wouldn't even have to create this intermediate value. We could just say this, and that would become the result, and it would return that for us. Yes?
And what if you would have yielded a different type in each iteration? What would be the result?
Yeah, okay, so what would happen if this yield produced multiple different types? This kind of blows your mind when you start experimenting with this in Scala. It figures out what the common type is, and if we were using, I mean, in this case, since I specified that the return type was a vector of int, I would get an error message because it wouldn't agree with my return type. But if I use type inference, it actually figures out what the common type is. The type hierarchy is much better than what you have in Java. So you do have a unified type hierarchy, and it would say, all right, this is something that is common with all those types that you're producing. Or if it couldn't figure out, it would turn it into a vector of any, which is basically object. But when you start trying to trick it and it keeps figuring it out, it's like you realize the people who have designed this are way cleverer than people who have designed some of the previous programming languages. It's really, it kind of blows your mind when you see it work. Okay, so here's another one. All right, I pointed out that I didn't actually have to create a result. Here's one where I don't create the result. I just say this whole for expression is the function body. Indeed, I would not even have to have these curly braces here because it's a single expression within the curly braces. So there's already just one expression. The curly braces are there to allow for a compound expression. But again, we didn't want to get into that quite this early. So here's my for expression. Take every element out of V. That's interesting. For some reason, we started adding semicolons in this one, which I don't think is necessary. Nothing like giving it in a presentation to see all your little glitches. So anyway, we're getting every element from my input vector. It's got to be less than 10. It checks, or it creates this. Notice what I'm doing here is within the for expression, I'm actually defining a new val. It's taking care of that for me. It recognizes that I'm defining something new here. And this becomes a Boolean expression, and then I say if is odd, and that is the result of this for expression. No, I'm sorry, that's not the result. That's part of this string of tests. And then if all of those things are true, then it yields n, and this is my entire expression. So after it's finished with this, it has produced this vector of ints. That's the result. And we can also put these things inside of curly braces. So this is the same thing that you saw before. The curly braces, again, are just a way to create an expression, and a compound expression in this case. And that's just to point out that you can use curly braces sometimes. All right. How much time do I have left, do you know? 10 minutes. Okay. Well, the nice thing about this is that I can just go until the time is up, because the way we've stepped it is just each thing, ideally, each thing just follows from the last, and however far we get is how far we get. I was not intending to try and get through the entire book this evening, but that's okay. We've actually gotten further than I thought we would. Okay, so as I mentioned to one of your questions, there's another keyword called any, which allows you to put, it's basically the equivalent of Java's object. It allows you to put any type in here. So my function accept anything will take an any and return a string, and then we do a pattern match on that. All right, so it comes in as an unknown type, and what pattern matching can do is it can match it against types, which is what it's doing here. It's say, is this a string? Okay, return a string. And now that we've talked about the rocket, you have a little suspicion that this may be an anonymous function, which is actually the case. We don't have to think about that, but that's just a little bit of an aside here. We can think of it as just, if I get one of these, then do this thing. Notice also that there is there's no need for a break statement. Again, that's kind of noise that we don't need to have. So here, X is different types, and I can match against the type, and then if it doesn't fit with, oh, okay. So here is my case class for person. That's interesting. I defined it after I see. This is the function. All right, this should have curly, it doesn't have to have curly braces around it, but for our own consistency, we wanted to put all functions within curly braces, and this one doesn't. This is why the book isn't ready yet. So anyway, it is a single expression, so we can just assign it to our function. It works, it compiles and it runs, but for consistency's sake, we wanted to put everything inside of curly braces until we defined that little bit of magic that you could do. Okay, so this is instead of having to do other types of type checking, we can just use case statements. Pattern matching. And here's a case class, person, the name, and then I can create a person and pass it to accept anything. It is kind of interesting, even though this is a script, the fact that this definition can be created before person has been defined. So it takes care of that kind of thing for you. I shouldn't be that surprised, but sometimes I am. Some languages are more particular about that than others. As long as it's got the definition somewhere before it tries to run it, it's okay. Okay. Okay, and it doesn't know what a vector is. Well, I mentioned that one of the main reasons for having case classes is to be able to use them for pattern matching. because it can create some very elegant code. So let's see an example of that, and that'll be our final example for this kind of introduction. So I'm going to create a passenger, a train, and a bus. So the passenger has a first name and a last name. The train contains a vector of passengers called travelers, and the line is the train line that the train is actually running on. A bus also contains a vector of passenger, and a bus will say how many passengers can the bus hold. Okay, here's a function called travel. It can take any type of transport, and then it matches the transport with a train, a bus, a passenger, or something called a thingamajig. Where the heck did thingamajig come from? I don't remember that. Case thingamajig. Okay, that's really interesting. That's escaping me right now how that works. Anyway, we take our transport and we match it. And notice that I can match the transport with not only the class name, but also the arguments in it. It will actually pull those out for me. So I can print out the line and the travelers. And it just, because it's a case class, it just automatically sucks those out. You can write those yourself explicitly in an ordinary class, but the case class does all that work for you. So if I pass in a train that has this many travelers in this line, I can just use those values without doing any extra work. This can be very helpful. The same with bus. Here's a passenger. Notice I don't give the passenger, even though passenger has the possibility of these arguments, so I could use it to deconstruct it. I don't. I'm still trying to figure out what happens with that. That is confusing to me. I don't remember putting that code in, so my co-author may have stuck that in. One of the things we're doing, we live many states apart, and we're using Google Docs to do this. So we have a single document, and we can both be working on it at the same time. It's very helpful, but I can't remember putting that in myself, so I wonder if she didn't do it. So I'm going to create a vector of passengers. Those of you who are movie buffs may recognize these names. And then I'll create a trip, which is a vector. Yes?
I was just wondering, what you said earlier that, over here, by the way.
Yes. Oh, yes, okay.
Sorry, disconcerting. Well, you showed that case statement with the thingamajig, and if that's an anonymous function, isn't thingamajig just a name for the parameter, so it doesn't have to be defined earlier?
Apparently, because this code does compile and run. I mean, the script runs, but...
I mean, that just seems logical.
Yeah, I guess so. It just... Well, there's got to be text in the book to describe this, or at least I hope there is, but... Yeah, anyway, well, let's just skip that for now, because I can't remember what... Or maybe I just haven't reviewed that code at this point. I'm kind of surprised. I mean, it does surprise me sometimes. And Scala is obviously doing something intelligent in that case. Actually, let's just double check that. Let's run that code. Let's see, quit. So. Case. Okay, let's just make sure it does run, because maybe it'll tell us. One of the issues is that the startup time for the interpreter can be a little long, and I'm pretty sure they're working on that. No, it's happy with that, so it's okay. Anyway, so I'm creating, let's see, down here. So I create a vector of travelers. I create a trip, which is a vector of, so the travelers first they go on a train and then they go on a bus, and so this simply compares trip 0 and trip 1. So here they're on the train and here they're on the bus for trip 1. So I guess mostly what I wanted to show here, we're working our way up to showing how quickly you can create complex structures without a lot of code complexity. The code tends to remain fairly readable. If you imagine doing something like this in Java, you're going to have a lot more code and it's going to be a lot less easy to scan. So I am down to 1 minute, so I'll bring it to close with that. The book should come out we're hoping this fall, and it'll be out as an ebook first, so it'll be available globally right away. If you have to have a print book, you'll need to wait for a while, but at least the ebook will be available basically as soon as we publish it. In English, yes, sorry about that. We're working on how we're going to deal with foreign translations, but at least for those of you in this room, obviously you can understand English, so you'll be able to get your hands on it as soon as we publish it. Thank you.